This is 8.1.2 alpha, beta, and gamma radiation. So first we need to talk about the properties. So we'll start with alpha, which is a helium nucleus in nature. So we can write it as 4,2He or 4,2 alpha, which means that it's got 2 protons and 2 neutrons. Alpha is a good ionizer. Because it's doubly charged, it can rip electrons out from other atoms. For example, in the air, when it's moving through the air. It loses all of its energy while it bumps into these molecules in air in about 4 centimeters and ionizes them. So it loses all EK in about 4 centimeters in air. And it's ionizing the air while it's flying through it. After it's ionized the air, at that point it's ripped the electrons off. It's got its own 2 electrons now, and it's just become a helium atom. So at that point, it's not moving fast, it's not charged anymore, so it just becomes a regular helium atom. In a cloud chamber, you'll see these as looking like thick, straight tracks. Because alpha is heavy in comparison to beta and gamma, in a cloud chamber, you'll see them as thick tracks, and they'll be quite short tracks as well. So tracks are thick and straight in a cloud chamber. Because they are massive in comparison. So it can be stopped by paper or skin. So it's not very penetrating. So it can be stopped by paper or skin. Now to detect alpha, we can have it fly through a magnetic field, and we put a detector on one side. If it flies through a magnetic field, because alpha is charged and it's positively charged, then when it goes through a magnetic field, it should deflect according to its charge. So let's draw an arbitrary magnetic field. And again, as usual, we'll draw a uniform field. And we'll have a beam of alpha particles flying into the field. Now if you apply Fleming's left-hand rule, then we see that the field lines are into the paper. The current is towards the right in the same direction as alpha because alpha is positive. And so the force experienced by alpha as it enters this field is going to be to deflect upwards. So if this alpha deflects upwards, and it's able to leave that field very soon, so we want it to be able to leave the field, then we place the detector around here. And we can move the detector around because you might not pick it up in one go. So we can move it left, right, a little bit to the side until we detect it. But what we will not do is bring the detector down. If we bring the detector down, then something that deflected downwards must have been negatively charged. So it won't be alpha that we're detecting if we detect it at the bottom. So alpha curves upwards as it is positive. And I'll put in brackets here, beta would be down, would curve down. Okay. Let's move on to beta. So beta could be one or two types. It could be the regular beta, beta minus, or it could be a positron, beta plus. So we've got beta minus, which is the electron, or its antiparticle, beta plus, which is a positron. So the beta particle is a high speed, which means high energy. High speed, I'll put in brackets, energy. Electron or positron. They come from the nucleus. So this is quite an important distinction to make, because oftentimes there's a misconception that because we're dealing with electrons, that they've come from one of the electron shells. But if we recall back to particle physics, we'll remember that beta is produced by a nucleus that decays. So for example, you've got the neutron decays into a proton. It also produces a beta particle and an antineutrino. And that conserves the lepton number, it conserves the baryon number, and it conserves charge. It's moderately ionizing. Has a range of about 10 meters, 2 to 10 meters in air. So they can vary quite a bit. And it's got moderate penetration. But it can be stopped by sheet metal. So for example, a sufficiently thick aluminium foil. And again, it depends on the energy of the electron. So some beta particles can penetrate better than others. But certainly if I had a sheet of metal that was a few millimeters thick, then that would be sufficient to stop it. If I had, for example, just foil, kitchen foil that was cut straight, that might block some beta, but some beta might still be able to get through that, depending on the energy that they had. So for beta to detect it, if we had a magnetic field, beta minus particles would curve downwards, and our beta plus particles would curve upwards. So again, we use the left-hand rule. The negatives go down, the positives go up. So we have to recall again the equation for beta decay. And so for beta minus, you've got a neutron, which decays into a proton, plus gives us a beta particle, plus an anti-neutrino, which is an electron type. Now, because the anti-neutrino's got 0, 0, sometimes you wish to just omit putting the numbers in at all. But you can see here that the numbers add up. Yeah, the numbers are conserved here. The Feynman diagram for this is a neutron, which turns into a proton, and then releases two other particles, which is the beta minus and the anti-neutrino. Now, by convention, antiparticles are drawn with their arrows facing backwards. However, at A level, you will not be penalized for drawing them facing forwards. So it doesn't actually matter if you draw them facing forwards or not. Now, in this Feynman diagram that I've drawn, you can see that the boson is slanted in such a way that as time evolves, it's negative charge leaving the neutron. So it must be carried by a boson that's got negative charge, so that would be the W minus. So W minus carries the negative charge away. So W minus is the gauge boson, and it carries negative charge away from the neutron. Next, we've got the gamma. So gamma is a photon, which means that it has 0 for nucleon number, 0 for proton number. It has no mass, it has no charge. So gamma is a photon. And since it's a photon, it moves at the speed of light. Which is 3 times 10 to the 8 meters per second. It has no mass at all. And it's got the highest penetration of the three. Highest penetration. It is not stopped. Rather, it's attenuated, which means it's weakened. So we can weaken it to the point of not having to care about it by using thick concrete or lead. So it's not stopped, rather attenuated, which means to be weakened. And we do that by using thick concrete or lead. So when you have a source that emits gamma radiation, we store them in lead-lined boxes in order to weaken the amount of radiation that's actually coming out of them. Now, the penetration or the range of gamma is basically infinite. So the range is pretty much infinite. It will keep carrying on until it's basically been absorbed. It's the least ionizing of the three. And it's produced when a nucleus is excited and the nucleus de-excites. So similar to electrons, how electrons can become excited and de-excite, they emit a photon of some frequency, and that frequency corresponds to its energy levels that's jumped down by. If we think of a nucleus, when a nucleus is excited, the amount of energy that it takes to excite a nucleus is a massive amount of energy. So when a nucleus de-excites, that gives us a huge amount of energy, which in turn means that there's a huge amount of frequency. So gamma photons have very, very, very high frequency. If you compare it to something nearer to it, so like an X-ray, you'll see like it's just much, much higher. Compare it to visible light, again, they're very, very high. So it comes from an excited nucleus de-exciting. And through de-excitation, that nucleus then becomes stable. Now, start a new page. All of these radioactive decay follow the inverse square law, which basically means that the intensity that lands upon some object decreases as 1 over r squared. So if you double the distance, the amount of radiation that actually lands upon something that's placed in front of it, rather than being halved, it's a quartered. If you triple the distance, the amount of radiation landing on that object is 1 over 9, etc. This applies to most things. So for example, during the COVID pandemic, you were told to keep 2 meters away. That was a social distancing rule. And the reason for that is, say if someone were to sneeze, if you were 1 meter away versus 2 meters away, the amount of stuff that would land on you by moving from 1 meter to 2 meters doesn't halve but quarters. Because as things move outwards, they spread out. So their intensity is reduced. So do the inverse square law. So for this, we'll do I is equal to k over x squared. So I is the intensity, which will be measured in watts per meter squared. K is just some constant, and x is the radius, or we can replace this with r as well, which is measured in meters. Now we have some constant because the amount of emission changes depending on what we're looking at. So K will depend on how much is being emitted. If you have lots of emission per second, then K will be a larger value. If you had very small amounts of emission per second, then K would be less. So we can think of intensity as the amount of radiation falling on a surface per second. Sorry, per unit area. Amount of radiation falling on a surface per unit area per second. So in other words, how many of these photons are actually landing upon that surface? Because every time a photon lands, some energy is given. Now, if you just have one photon land, that's some energy given. And then if you have a period where no photons are landing, then the amount of energy per second is reduced. Whereas if you have a constant stream of these photons coming in, then that's a lot of energy landing per second. So the more exposure you have to these things, the greater the chance of becoming ionized. So you're not going to avoid gamma radiation entirely, but you reduce your exposure to it as the probability of having ionization occur increases as there's more exposure to it, or as more photons are incident upon you or upon that surface. Okay, we'll talk about background radiation next. Background radiation is very relevant when we're doing any experimentation on radioactivity. So if I took a Geiger counter and I placed it in this room right now, we don't have any radioactive sources in the room. So in ideal conditions, we would hope that a Geiger counter will read 0. But actually, there's radiation everywhere all the time. So you might have a random atom in the air decide to decay, and a beta particle flies past. You might have some gamma that's stray from somewhere else flies past. You might have granite worktops that are emitting some amount of radiation. You might have a banana where some atoms in a banana are decaying and emitting radiation. So you'll always have some background. Now, if I were to then take a piece of paper, for example, that you and I know intuitively is not radioactive, we put it in front of the Geiger counter, and then I said, hey, look, this is the amount of radiation coming off that banana. That would be incorrect, because if I said banana, paper. If I then remove that paper and I count it again, I get the same amount of radiation. So we call that the background radiation. It's coming from the background, from other things. So when we're doing our experiments, we have to make sure we correct the count. So first, you would measure the background, then you would do your experiment with your radioactive source, and then you would correct the count rate by taking away the average background count rate that you've measured over a period of time. So our background radiation can come from rocks, or even cosmic rays from space. And again, these are small amounts. Can come from granite, so there's actually a recommendation that if you have granite worktops in your kitchen, you open your windows more often to let some of that out. So, when measuring background, we have to make sure that we keep our radioactive material far away from it. So typically, you want to keep them about, well, first you'll keep your background, your radioactive material sealed in their containers. You would then also try to move them as far away as possible, usually about 2 to 10 meters away. If you move it 2 to 10 meters away, you're sufficiently far enough that you're not going to be picking up any radiation from them to affect your background count. You can't remove them entirely from existence because they're always there. So for example, you're in a school. That school does have some radioactive material somewhere stored. You won't know where it is because you're not allowed to know where it is, but it's stored somewhere. And where it's stored, it should be sufficiently far away that it's not kept anywhere near where people spend a significant amount of time. So it would be kept in a place that's at least 2 meters or more away from any seating areas, or any place where people congregate, or any place where people stand for a significant amount of time. So that way, when you're in a lab and you're taking these measurements for background, you know that any radioactive sources stored in that building or in that institution is not affecting your results because they're stored significantly far away. So, we'll write this down. When measuring the background, keep sources far away. And I'll write from the GM tube, the Geiger-Müller tube. And then when taking a background reading, because radiation is random, you can't predict when it's going to happen. So if you take a reading for just a few seconds, you might not capture enough background radiation to say that this is the average background radiation. So you should do it for a significant amount of time. Now, significant amount of time can vary depending on what we're talking about. So typically 5–10 minutes of measuring background. So take readings for background over a long time, e.g., let's say about 300 seconds. Can be more. And also, we don't just want to take readings in one place, we want to move our GM tube around and take readings in a few different locations. So, and take several readings by moving the GM tube. Once you've done that, then you can work out the average background count rate, which you can then use to correct any count rates from your actual experiment. Now, for safety, you have to handle radioactive material safely. So, one thing you can do is wear protective clothing. So your protective clothing will be things like gloves. It would be lead-lined aprons. But in an educational setting, the sources are weak enough that you won't need to wear these. So protective clothing, e.g. gloves, lead-lined aprons. And the point of these is you never want to touch the sources directly. So never touch sources directly. The reason for that is there are two things that happen, and people often conflate these two things together. And we'll talk about these in more detail later on. So one thing is irradiation, how much radiation exposure you're getting. The closer you are to the source, the more irradiated you get. Okay? So if you touch a source, you're so close to it that more radiation falls upon that part of your body compared to if you were standing away from it. And even worse than that is, let's say a piece of that material breaks off, like a bit of dust falls off from that material and is now on your hands because you've touched it. That's now called contamination. Because now that you've got a piece of that material stuck to your hand that you haven't even noticed, as you're walking around going about your day afterwards, that material is constantly on your hand, constantly irradiating you further. So now you're a walking radioactive source as well, because that little bit of dust on your finger is emitting some radiation. And most of that radiation is falling upon you. And exposed for a significant amount of time, that could lead to ionization and mutations of your cells. So the difference here is you can irradiate something and that object does not become radioactive itself. Yeah? So a lot of times people think if something has become irradiated, radiation has fallen on that object also becomes radioactive, but that's not true. It's if it has been contaminated with that radioactive material, then that object becomes radioactive, because it's carrying the radioactive material around with it. So, we still need to handle the materials, move them around, place them in certain places. So when we're doing this, rather than using our hands to do it, we would use equipment that gives us some distance away from it. So we'd use long tweezers to pick up and handle the material. So for example, if we had long tweezers that were more than 4 centimeters long, well, alpha's not going to reach us at all, because alpha's got a range of 4 centimeters. And we could do the maths here as well. If we use tweezers that were twice as long as standard tweezers, well then that's only 1/4 of the radiation that falls upon your hands. So you've quartered the amount of exposure that you get. If you had tweezers that were triple the length of your traditional tweezers, your regular tweezers, you've 1/9 the amount of exposure that you're having. So when we're using these, we also consider the inverse square law. At all times. So what this really means is, If we're taking measurements, we've placed our source on our GM tube, for example, or we've mounted it on some device some distance away from the GM tube, at that point, we leave it alone and the measurements are happening automatically. It's better to take a step back at that point and keep a larger distance between yourself and the source. So stay further away whilst not actively handling the source. Okay, so when we consider the inverse square law while we're handling radioactive materials, you make sure that if you're not handling the materials directly or actively, you take your measurements, take a step back so that that distance that you put between yourselves and the source will decrease the amount of exposure that you get. Okay? So, next we'll talk about intensity. We mentioned this earlier, that intensity is measured in watts per meter squared. But for practical units is the counts. So the amount of radiation that actually lands. So that's measured in something called becquerels, BQ. So rather than measuring the actual amount of energy received, we look at how much radiation is received instead. For radiation, a practical unit is the becquerel. Is the becquerel, which is BQ. And BQ means the counts per second. So how much radiation you count per second. For radiation, a practical unit is the becquerel, which is BQ, which means the counts per second.
So how many radiation?
If you count 4 per second, it's 4 BQ. If you count 20 per second, it's 20 BQ. All right, we start a new page, and we'll go through the inverse square law practical. And this is one of the 12 required practical activities in A-level physics. So we've got a track. And we've got a source on the track. Then we connect a counter to our GM tube. This is what the experiment will look like. Now before doing this experiment, we have to make sure that we have our background count rate. Because when we do the experiment, we have to make sure we correct our count rates. This is especially important as we move the source further and further away from the GM tube, because at that point the background radiation will at some point become comparable to the radiation from the source. So we start with measure the background without the source. Many times, then calculate average. Next, we place the source on the track. We need to measure its separation to the GM tube. And measure the counts over some time, say for example 100 seconds. Then we can calculate the count rate. We repeat this several times by varying the distance. So vary the separation and repeat several times. E.g., greater than 7 sets of data. Then we have to do the count rate that we calculated minus the background count rate to give us the corrected count rate. So calculate the corrected count rate. Or the count rates, because we have multiple sets of data. Next, we can calculate all the values for 1 over r squared or 1 over x squared, whichever variable you choose to use. Now, if we plot the count rate against 1 over r squared, we should get a straight line. Because if intensity is proportional to 1 over r squared, and intensity is also proportional to the count rate, because again, it's energy per second per unit area. So if it's energy per second, that also means, say if we average out all the radiation, and we say that pretty much all the radiation gives us the same amount of energy, approximately, then the more radiation that lands per second, the bigger the intensity is. So that makes sense. So I equals to k over r squared. So if we plot count rate on y and 1 over r squared on x, we should get a linear graph. And that shows us that it indeed does follow the inverse square law. Once we've got this graph, we can calculate that constant k by doing the gradient. And so that experiment has successfully shown us that this radiation source, or gamma, follows the inverse square law. And that's the end of 8.1.2.